So on behalf of the Department of Computer Science Engineering, NIT Puducherry, I welcome you all for the 5th session of the 5 days online Atal FTP in recent advancement in social Internet of Things and industrial Internet of Things in the topic Security Algorithm for SIoT and IIoT applications. I invite Dr. Narendran Rajagopalan sir to take over the session. Thank you.
Thank you, madam. Oh, is my screen visible?
Yes, sir, it is visible.
This is going to be the fifth session of this FTP. It is based upon the security aspect or with this quote, let us start where Internet of Things becomes devoid of comprehensive security management. Yes.
Excuse me, sir. Sir, your video is switched on, sir, but it is not properly placed. We cannot see.
Okay.
Okay, sir.
Okay, let me turn off the video basically. Which basically tells that Internet of Things basically becomes invaluable, or it's not of much use if we are not able to put in security in place. It becomes Internet of Threats. This is one of the prime reasons because of which IoT acceptance has been repelled. So this is going to be the outline of the presentation today. Introduction to what actually is security. Then we will discuss upon network security. Then how is IoT security different from network security? Whatever be the security, at the end of it, it falls upon the basics of cryptographic algorithms. Then some frameworks in the IoT domain where this security is being implemented. Then we'll look at what actually are some things which actually do not cover under these algorithms, how it is being addressed by intrusion detection system. Then we'll just have a very small introduction of blockchain. Then how does it impact in a SIoT network? So this would be the outline of the presentation today. The significance of IoT or security in IoT. Basically, IoT is a combination of heterogeneous collection of too many things which are being produced by different vendors. So the market is not a regulated one. There is no standardization being followed. When there is no standardization, there is always room for loopholes which can be exploited. There has already been a incident where a D-Link home router had a vulnerability in its software, which was about 2 years old. And this was exploited with the Satori malware attack. Worms are basically a kind of programs which actually would replicate by itself. Even the Mirai malware attack, it has tried to just by trial and error method, it has tried using the default passwords or very commonly used words as username and password. And surprisingly, it has been able to log into millions of devices, which actually shows that people don't change the default username password, or else even if they do, they keep the username password to be very common one, which can be guessed or uh, tried by brute force method. Okay, with this they have been able to successfully launch a distributed denial of service attack in the year 2016 itself. The number of malware attack on IoT devices has shown an increase of about 66%, with 57 million attacks in the year 2020. The number of attacks was around 33 million in the year 2019. So it's increasing by a very huge margin year on year. Basically, any network security would wish to address these three triad of network security. This is called as the triad of network security, which consists of confidentiality. Confidentiality basically means only those who are authorized to access a certain information must be able to get it. And also, are they the one who are using it? That needs to be authenticated. So authentication and authorization happens to solve or address confidentiality. Then we have integrity. The information that is being transmitted or communicated is not getting affected in between or not changed. This is another goal of network security. And the other one is availability. There are data, there is resources or services. If a legitimate user is trying to access it, it must be available to him. These are the goals of network security. Now we will look at the goals of IoT security, which actually includes confidentiality, integrity and availability as part of the ones. But apart from that, there is also non-repudiation, which basically means someone who sends information then later should not retract saying that I did not send it. There should be a way by which he is some kind of auditing should be there, digital auditing, by which someone cannot backtrack from the actions performed. The same applies even for devices. Then you have privacy. There should be rules and policies in place, or it should facilitate rules and policies such that I am able to keep certain information as private. Auditability basically is being able to monitor and log the activities of IoT objects. Accountability is a opportunity by which the number of users that are using it and their actions are logged. Then we have trustworthiness, which basically means when a device is coming into an IoT environment, it is acting as an independent entity. And we need to actually assess and analyze the actions of the device to build upon a trust value. So it must be able to, that is the way even our social network works. We try to talk to people to understand and assess the reliability metric. The same should work even in the IoT domain. What are some of the security challenges in IoT? One is or else we don't give due importance to security. Security is seen as a afterthought. First, we think of developing and making the system work. In the process, sometimes we might program or else we might build the system such that it becomes rigid enough not to later incorporate security aspects, or else during the coding or programming phase, or else even hardware devices being placed, we might leave out upon some of the loopholes, which can later lead to security issues. So lack of secure development. Second is tight resource constraints. As we have already discussed even yesterday, IoT is an environment where energy plays a very important role, because of which your traditional security mechanisms, which would consume a lot of uh, computational resources and memory, cannot be used as it is in a IoT environment. That is one challenge. Design, basically IoT systems are designed for very specialized and specific tasks. Even security algorithms that we would be discussing today are very generic. But in industrial IoT, if you see, we build this IoT that is a generic model. We make it specialized for a specific industrial IoT application. When we make that specific application, we are supposed to study the environment in order to give even physical security to the system, IoT system, and we should be able to also look at other possible security flaws which is specific to the domain. So these are things which actually cannot be a very generic solution. One common security solution cannot be applied to all possible specific applications. Dynamics in security needs. Basically what it is trying to hint is, you have a car. When the car is stationary, you are more focused upon the anti-theft system. Whereas when the car becomes in motion, then anti-braking sensor is what is of more prominence or more precedence. So security needs changes with the dynamics. The way it is being placed, it depends upon each of the specific scenario, and it is time dependent also, or state dependent. That's why dynamics in security needs. These are some of the classes, generic classes of malicious software. One is the virus. I hope you would have heard about viruses, worms, trojans, and bots. Viruses are basically a small snippet of code which actually would get embedded with a bigger program, and it gets actually replicated only when there is a human intervention, or else the program to which it is embedded into is physically transferred. Worms are actually a subset of virus. specific subset of virus, but worms are independent programs. They are not a dependent one, and they self-replicate to different systems. Then we have Trojans. Trojans are basically.
Sir, excuse me, sir.
Yes.
Sir, some are telling that they are not able to see the PPT, sir. Can you present it again, sir?
Okay.
Okay, sir. Thank you, sir.
Is everyone able to see the PPT now?
Sir, for us it is fine. Neelakshi, ma'am, whether you are able to see now, ma'am? Yes, sir. Now it is visible, sir.
Okay.
We can carry on, sir. Thank you, sir.
Thank you. Yeah. Bots basically are automated processes that interact with other network resources. Which tries to do flooding type of attack based upon a specific target. Those were generic attacks. Now coming on to IoT specific issues. IoT is not only vulnerable with the software attacks, there is also hardware trojans based upon the IC configuration. Hackers can exploit the functionality and try accessing the software. There is also something called as an object replication, which tries to replicate object's identity. When an object's identity is replicated in a network, then the dynamics and the data flow itself gets confused. The routing itself gets affected, because of which the network performance suffers a huge slump. Then you have denial of service attack. This denial of service attack is something which is still being researched upon, because it is not pretty straightforward to understand and remove it. First thing, what does this? There are two types. One is the sleep deprivation. As you all know, IoT devices are power and memory constrained devices. If I do not allow a IoT device to sleep and I keep pinging it with a periodic message, then it will make the device to respond and it will be active. When it is active, actually it loses the power, because of which it the power dries up and it cannot work. Next is the outage attacks. Because of such sleep deprivation, there could be it wouldn't be able to respond back to the events that happens. This is something that has happened even with a real life scenario where Iran's nuclear system was affected with Stuxnet. With Stuxnet, actually the emergency alarm system which was in place in the nuclear system failed to respond when there was a actual outage. It did not alarm, or else did not take appropriate corrective measures. Then we have physical attack, where a hacker can extract the security features, modify the operating system, and vandalize the circuits. Next is the malicious node. With a malicious node, basically, you can try bringing in a node which actually doesn't work with the interest of all the other nodes, but upon a selfish interest or a predetermined interest, which would basically hamper the performance or degrade the performance of the actual network. Then we have the side channel attack, which basically by assessing or by observing a particular scenario, you would be able to imply some meaning or information out of it. Like a medical IoT object may unintentionally release sensitive information about the object as well as the patient. Like if there is an IoT device which actually is a heart replicator or artificial heart pump, then someone would be able to still understand that there is a heart patient available there. This kind of implication information that can be derived from observation is what actually is side channel attack. So what are the, so these are some of the issues or challenges. Now, how do you address each of it? One is we have cryptographic algorithms to do that. With cryptographic algorithms, you can address confidentiality, which, as I told, also includes authentication and authorization. Authentication is done. Non-repudiation, that is, a particular user does a certain action and later he cannot claim that he did not do it. And the other one is integrity, basically change of the message or information itself. These are things which are addressed by cryptographic algorithms. These are some of the very common, well-known, frequently used, successful cryptographic algorithms. They are classified into symmetric key cryptography and asymmetric key cryptography. And the other one is the hash algorithm. Under symmetric key cryptography, basically the encryption of the message digest is done with the same key, and to get a plain text is encrypted using a key K. To get a cipher text, the same key K is being used to decrypt the cipher text to the plain text. This is what actually is the definition of a symmetric key algorithm. In an asymmetric key cryptography, there is something called as a public key and a private key. A public key is shared and it is visible in the outside world. A private key is something which actually is held by the party. If someone wishes to send data to the party, he is going to actually try encrypting the message with the public key to get a cipher text, which will be transferred to the party. The party would be able to decrypt the message using the private key. No one else other than the person who is owning the private key can decrypt it. This is what is called as asymmetric key cryptography, where two different keys, a private key and a public key, is used for encryption and decryption. The advantage of this asymmetric key cryptography is it is also able to provide you with an authentication that the message is received only by the specific addressed recipient, because only the addressed recipient will have the private key. And this Diffie-Hellman key RSA algorithm and elliptic curve cryptography are some of the very commonly used asymmetric key cryptographic algorithms. Now, looking specific to the data encryption standard, this actually was introduced by IBM, and it is one of the oldest encryption algorithm. But unfortunately, it is susceptible to brute force attack. The key length that is used for encryption in a data encryption standard is around 64-bit key, but only about 56 bits are used, whereas the other 8 bits are dropped. Data encryption standard is based upon substitution and transposition, which is done with S box and P box, and about 16 rounds of such substitution and transposition takes place. In the year 1997, this DES algorithm was broken down in 56 hours. Sorry, it was broken, but in 1998 it was broken in 56 hours, which was improved to 22 hours in 1999, and which can be broken in about 5 minutes with the current processing capability of 2021. That is the reason actually data encryption standard has been phased out. Basically, there was also another improvement for data encryption standard with triple DES, with a bigger key, which was about 128-bit key, but that also lost its significance with time and has phased out. This advanced encryption standard is what is the most widely used encryption algorithm. It works upon a block size of about 128 bits. The key size is about its variable. It starts with 128 bits and goes up to 256 bits. It is based upon substitution permutation networks, and the number of rounds depends upon the key length. For a 128-bit key length, it works for about 10 rounds, whereas for 192 bits, it works for 12. And for 156 bits, it works for around 14 rounds, with each round having a substitution permutation network. Blowfish is another symmetric block cipher algorithm with about 64-bit. It handles block ciphering. A block of data of about 64 bits is taken and it tries to come up with a ciphertext, and it keeps on doing it, and it gets connected together. Blowfish algorithm is a open source encryption algorithm which is available in the public domain, and many claim that it is not yet broken. It is pretty user friendly and flexible for encryption. It is still being used for secure online payments and also to protect user passwords. So those were the three symmetric key algorithms. Now we'll look at a few asymmetric algorithms. One very widely used asymmetric encryption algorithm is the RSA algorithm, reverse Shamir-Altman algorithm. This was founded in the year 1977. The key length here is also variable, which starts with 768 bits, going up to 4098 bits. This RSA algorithm is being used in many of the IoT applications. This is also found wide usage and acceptance in the secure socket layer and transport layer security certifications. It is used for email encryption too. These are some of the applications of RSA algorithm. The next well-known algorithm is the digital signature algorithm, DSA, which was developed in the year 1991. It is another asymmetric encryption algorithm, which is relatively slow compared to RSA algorithm when it comes to encryption and signing. But when it comes to decryption and verification, DSA is able to be faster than RSA. So since encryption and decryption together is what a process of authentication as well as verifiability is implied, DSA algorithm is able to match the speed of RSA when it comes to the complete process. This algorithm is also used in IoT applications now. Next is the hashing algorithm, which basically is the most of you would have heard about message digest or else secure hashing algorithm SHA-128, SHA-256. Basically, hash algorithms tends to generate a fixed size length message from any length text, which we call it as a signature or else a hash key. And this is a one-way conversion function. Basically, from that plain text, you can arrive at a hash value. From that hash value, you can never go back to the text at all. This hashed value is normally enclosed as one of the parameters during the data transfer. When it reaches the other end, when it tries to find the hash value of the text, it must be able to match. If not, then you understand that the integrity of the message has been compromised. These are some of the applications of hashing algorithm, which is being used very effectively and efficiently in the IoT environment. Authentication protocols like there is transport layer security TLS, which basically has a set of cryptographic algorithm called as a cipher suit. Out of that cipher suit, the sender and the receiver, both of them come to an agreement upon what kind of a cipher algorithm to be chosen for in order to ensure authentication and confidentiality. This choice is being left up to the sender and receiver because some devices would be able to have a better processing capability and some devices might have a lesser processing capability. So a cipher suit might include a variety of cryptographic algorithms matching different capabilities. So this figure shows that it asks for a certificate. Upon mutual acceptance of the certificate, there is a secret key that is being encrypted and passed. This key, which actually is called as a session key, is what is used for encrypting of data. So just after that, that key doesn't exist anymore. So for each of the data exchange, there is a session key that is being exchanged between the server and the client. This transport layer security facilitates this process. So we looked at the cryptographic algorithms with TLS 1.2. It is basically a framework that is able to utilize the cryptographic algorithms and other uh, security to give a secure environment. The same applies even with this IPsec. This is actually a framework which includes a set of protocols for security at the network layer. Initially, this IPsec was built exclusively to give VPN or virtual private network connectivity. But with IPv6, IPsec has been made a mandatory requirement. With IoT, IPv6 is what is going to be used, and because IPv6 makes IPsec a mandatory requirement, this is a very viable framework which can provide and also sustain the security vulnerabilities in the IoT network. Basically, IPsec provides you with IP security provides you with two choices of security service. One is called the authentication header, which just authenticates the sender of the data. And the other one is encapsulating the security payload, ESP, which does the authentication of the sender and also encryption of data. So if you want it to be lightweight, you are not able to have the computation or processing ability, then you can actually go for an authentication header type. If the data that you are transferring is very sensitive, then you can go for, and also the processing capability that you have is good enough, then you can go for encapsulating or encapsulated security payload, ESP. When we want to use IPsec for IoT, we discussed one is the cryptographic algorithms, which actually happens to be one concrete block. Then we looked at a framework for IoT like IPsec, TLS. Now, key exchange is another very important aspect. There are specific algorithms dedicated for key exchange itself, like internet key exchange, IKE v2, and host identity protocol. These are some of the protocols that are used to exchange keys with authentication. There is also extensible authentication protocol which encapsulates multiple authentication methods. So based upon specific use cases, specific scenarios, you can pull out any one of the authentication method and use it. So EAP provides you with a suite of authentication methods. EAP normally operates at the data link layer. There is another protocol called as protocol for carrying authentication for network access called as PINA, which enables network access authentication between the clients and network infrastructure. IPsec in the transport mode is able to provide you with authentication and uh, replay protection services in addition to confidentiality and integrity. So we looked at TLS as a framework. We looked at IPsec, which actually is a TLS is a transport layer security framework. IPsec is a network layer security framework. Then we have wireless HART. This is basically a network and a data link layer security solution. Wireless HART is a secure protocol suited for IoT. Payload is encrypted and all messages are basically authenticated, whether it is a single hop message or else a end to end. As per the standards of wireless HART, all devices should have a secret key and a network ID. Only if a node has a secret key and a network ID, it can join a network. So during the setup phase itself, these parameters are set. This wireless HART is primarily designed for industrial process automation and control. Basically, it is for industrial IIoT. Any new device which wishes to connect would be provided with a join key. With this join key, basically it is authenticated. Once this authentication is successfully done, the network manager provides that entity or the device with a session and a network key. This session key is for end-to-end communication between any two nodes. It can be a node to node or else a node to a gateway. Gateway basically is a node which actually connects to a bigger network or else just like how a router is. So all data that flows out of a one hop would be via a gateway. The data link layer DLL uses a network key to authenticate messages on a one hop basis. So effectively there are three keys. One is the join key, which actually is the secret key, which is set up for each of the nodes that are connected to that are initially installed in a network. It is with this join key that it is authenticated. Once that is done, a network manager basically is a trusted entity which would provide with a session key and a network key. These are the two keys which are temporary keys provided for communication. In this, the session key is used for transport layer end-to-end encryption, and network key is used for one hop communication. Now looking at the Zigbee security solution, which actually is very similar to how wireless HART is. Zigbee basically includes access control list, frame counters, and encryption of the communication that happens over the air. Zigbee as a security standard mandates advanced encryption standard with 128-bit key, similar to how with the previous one you had network manager. Here you will be having a trust center. So every node should be authenticated by the trust center to join a network. So once the trust center is able to authenticate a device by its ID, the trust center will send a network key to encrypt and decrypt general protocol data. This network key can be used for encryption of control information and also data. There is also something called as a link key, which is provided by the trust center. Trust center provides network key as well as link key. Link key is basically dedicated between two nodes for unique and exclusive communication, which may not be via a gateway. At times, if you wish to still communicate it via gateway, then you can use two-tier security where actual data is being encrypted by the link key as well as the network key. So once when it passes via a gateway, the gateway will be able to decrypt it with the network key, but still it will not be able to make sense out of the data because the payload is now in a encrypted form with link key. So it will again forward that data to the receiver. The receiver which has the link key will be able to decrypt it. Between Zigbee and wireless HART, in terms of security aspect, wireless HART is considered to be superior to the security options or facilities provided in Zigbee. With Wi-Fi, we have wireless equivalent privacy. Then we have which actually was wired equivalent privacy. It tried to give the privacy which was equivalent to a Ethernet wired LAN. It used reverse cipher RC4, and the session key size was about 40 bit. The cipher type is stream cipher, and the data integrity check was done with the cyclic redundancy check of 32 bits. Key management was not supported with the wired equivalent privacy. WEP had many flaws, and with a man in the middle attack, they were able to overcome the security. they were able to break the WEP functionality. So it ceased to exist, and WPA came into existence in the year 2003. Even though it also used reversed RC4, it was able to improve the security with temporal key integrity protocol. And also the security was enhanced because of the session key size being increased to 128 bit. The cipher type was still stream based. Message integrity code was used for checking the data integrity. Key management was provided with the 4-way handshaking mechanism. For a specific session, key was being exchanged, and that was used for encryption and decryption. Then in the year 2004, WPA was revamped with advanced encryption standard as the encryption method, along with CCMP. Apart from that, except for the cipher type being changed from stream to block, there is not much of a big change. With WPA3, which came into existence in 2018, CCMP was removed and solely the encryption method has been advanced encryption standard. And the session key size is kept variable for personal use configuration. WPA3 supports 128 bit, and for enterprise edition of WPA, the session key size increases to around 192 bits. Data integrity has also changed from CBC MAC to secure hashing algorithm, SHA. So these are some of the frameworks that are in place for IoT, which actually can be specialized or specifically designed for particular IIoT applications. But there are certain aspects which cannot, like a internal node acting maliciously with cryptography and all, external node not being able to get the information. You are able to do that. Cryptography basically helps with external attacks. Internal attack, where a node which belongs to your own network performs maliciously, is something which cannot be addressed by cryptography. So we have something called as the intrusion detection system, which tries to observe the functionality of a particular node, collect data, analyze the data, and raise an alarm for it. So basically, intrusion detection systems are, along with cryptography, tries to give you a complete solution, two-tier solution for any security aspect. When we talk of intrusion detection system, there are three types. One is the signature based, which basically is the one which is very predominantly used, which is also known as misuse, which tries to look for patterns. If the pattern matches, then it raises a security alarm. This signature based can lead to a lot of false positives, which basically means you can end up with a security alarm, even though it may not be the case, just because there has been a match. Then we have anomaly-based intrusion detection system, where the network and computer operations are monitored. If the operation is going out of the normal state, then it is considered to be anomalous and appropriate steps are taken. Anomaly-based IDS is mostly based upon machine learning, based learning high computational overhead based methods. So is even with the specification based ones. This blockchain is considered to be one of the promising technology for some of the security aspects in IoT, which can be as specific as trying to store certain data. If you are not keen with having a centralized data storage, or you don't want a physically visible data center, then such options can help you. One is the property of a blockchain is basically is an automated distributed ledger mechanism, which is able to offer solution for IoT security. It protects against data tampering, locking access to IoT devices, and it can also try shutting down some compromised devices. Blockchain is basically based upon distributed consensus and anonymity characteristics. It is a sequence of hashed chain records. This has found widespread use in smart contract, smart property. The only limitations of a blockchain being used in the IoT scenario is the amount of computation that the blockchain demands. There is work that is happening in the domain of blockchain to change from that proof of work or proof of stake to proof of storage to lightweight mining algorithms by which the storage as well as the computational cost is minimized so that it's able to find widespread application in the IoT domain. When we talk of SIoT, even yesterday we discussed about object profiling. Basically, SIoT is nothing but the combination of social networking with IoT. So all these security algorithms that we studied in IoT are generic algorithms that also applies for IIoT and SIoT. Apart from that algorithms, there is also object profiling, owner access control, trust management, in which the social network objects or blockjets that we call needs to be profiled properly. If we are not able to profile it properly, or else we are not able to set the owner access control for the devices, the settings for all these devices, and have a proper defined trust management module in place, okay, then SIoT will not work. along with all these different security algorithms that we studied, these play a very major role. If in spite of using all those security algorithms, encryption, decryption, everything, if we do not do the object profiling or owner access control, then we will end up like this. In spite of having all the armor in place, we don't configure it well, then it would lead to incident like this. So with this, I complete the presentation for this. If you have any questions, you can ask.
Dear participants, if you have any doubt, you can ask, sir. Any queries? Participants, any queries? Sir, can we conclude the session, sir?
Okay, madam. You can conclude it.
Okay, sir. Security is a process, not a product. Safety and security don't just happen. They are the result of collective consensus and public investment. As sir said, configuration is very much important on our side. The presentation was very much informative, sir, with all algorithm defined, concentrating the security aspects. It will be very much helpful for the researchers to think and implement in their work. It was a pleasure to listen to your consistent presentation, which is very much clear. On behalf of the Department of CSE, NIT Puducherry, we are very much thankful to the time you took to share your knowledge, sir. Thank you so much.